In this screencast, we look at the fourth of the colligative properties. This would be number 4. The first one, of course, was vapor pressure with Raoult's law. The second one was boiling point elevation. Raoult's law said that the vapor pressure would go down, interfering with the ability of a solvent to evaporate. The boiling point elevation is because your solute would interfere with the ability of the solvent to go into the gaseous state. Then we talked about the freezing point depression, because the solute would interfere with the ability of the solvent to crystallize, and so the temperature has to be lower before it'll finally freeze. And number 4 is osmotic pressure. And of course, it comes from the word osmosis, which is used an awful lot in biological systems. It's defined as the movement of solvent molecules, and for our purposes, most of the time that's going to be water. When we think about aqueous environments, the ocean, but also the aqueous environments of human cells and tissue and blood. Through a semi-permeable membrane, a semi-permeable is sometimes called a differentially permeable membrane. And what is implied by semi-permeable or differentially permeable is that it's selective. It allows some particles to travel through the pores or openings in the membrane, and other particles cannot travel through, generally because they're too big. So it's selective in that respect. And so what naturally happens is things move from a region of low concentration. The movement of a solvent molecules through a semi-permeable membrane from a region of a lower solute concentration to a region of higher solute concentration. This is the solvent that is doing the movement, not the solute. So if we look at these two pictures right here, here we have a high concentration of water that is inside the membrane. And this is the membrane right here. And we have a low concentration of water. On the outside, we have a high concentration of the water, and we have a low concentration of the solute. In fact, it's 0 because it's pure water. So here we have low concentration of a lower concentration of the water compared to the higher concentration of the water outside, and we have a high concentration of the solute compared to the lower concentration of the solute outside the membrane. Now, the idea here is that the pores or openings in the membrane allow water molecules, which are quite small, to travel through them in both directions. They can move in, they can move out, and they do so evenly when it's at equilibrium, of course. Meanwhile, the salt particles can't get through the membrane. They're too big. Those sodium ions and chloride ions, or whatever they are, can't get through the membrane. So as a result, even though normally you would think that the salt particles would want to go from high concentration, let's change colors here, from high concentration out to the low concentration, they can't. It's blocked. So there is a net flow of water in. The solute cannot get out, but the solvent comes in. And as a result, that membrane begins to inflate. And we have this picture over here. And on the right side. And you can see that as water is flowing in, the water begins to move up this tube until eventually it levels off. Now, the reason it levels off is because all this water in the tube has a certain weight, a force of weight, and it's pushing down on this surface area. And the force of weight per area exerts a pressure downward, and the water that's flowing in exerts a pressure upward. And when those two pressures are equal and opposite, the water stops rising up the capillary tube, and you reach a state of equilibrium. And the way we measure the osmotic pressure is to measure the height of this column, again, in millimeters of water, which can be converted into millimeters of mercury by dividing by 13.6, because mercury is 13.6 times denser than water, and that gives us millimeters of mercury. And of course, millimeters of mercury, which is the same thing as a torr, we can convert into atmospheres, because there's 760 millimeters of mercury in an atmosphere, or we can convert it straight into pascals of pressure. And that would be the osmotic pressure. Again, keep in mind that the water molecules, being small, they can move both ways until the pressure to go either way equals out, and then you're at equilibrium. But the larger particles cannot move, and so the net flow of water into the membrane is what creates this osmotic pressure. Now notice the symbol for osmotic pressure is the capital pi, not to be confused with lowercase pi, which we use when we talk about circumference, 2 pi r, or area of a circle, pi r squared, for example. Now, if we take PV equals nert, our ideal gas law, and we say, instead of thinking about all these particles that are moving around as being gas particles with just space in between them, we think about these being particles that are moving around randomly within the solvent. We end up with a very similar equation. If I divide both sides of my equation by volume, my volumes cancel out, so I'll erase the volumes, leaving me with just pressure. Then, if we recognize that moles over volume is molarity, represented here by C, the concentration, and instead of talking about pressure, which is we usually use for gases, we use this for osmotic pressure, you get this equation right here. So you can see how it's connected to PV equals nert. It's analogous to it. And we're still using the ideal gas law constant, R, which is 0.0821 if we want our answer in atmospheres. You can use one of the other constant if you want your answer in millimeters of mercury, or pascals, or bars, or millibars. And this picture right here kind of gives you an idea of a channel, a hole in the membrane. So the membrane is this whole thing here, and these are channels or holes. And in a cell wall, these would be holes or pores through which molecules can move naturally from high concentration to low concentration. You might remember that from biology. Now, just as if we were to allow this system to operate naturally, fresh water would go from high concentration to lower concentration, in comparison, the salts or whatever the impurities are in the left side of this container can't get through the membrane. They're blocked because they're too big. So the water would flow from the right to the left, and it would push up on this piston. And we could measure that with a certain amount of pressure. That's what would happen naturally. But let's say we take this piston and instead we're going to push down on it. When we do that, we're going to make everything move in the opposite direction. So when we push down on it, that's going to force the water molecules to move in the opposite direction, which is this way. And so the solution in here is going to become more and more concentrated as the solvent, the water, leaves, but the amount of solute stays the same. And so your numerator in moles per liter gets bigger and bigger. The concentration gets greater and greater. Periodically, in reverse osmosis, you just get rid of that highly concentrated salt or impure water, and then you put in a fresh batch of ocean water or a fresh batch of water if you're hiking in the mountains or somewhere. You're not sure if the water is pure or not. You put the water into here. You use your hand to push down, or commercially you would have a machine operating a hydraulic press to push down, and that would force the fresh water to come to the right. And this is the water that you would be able to drink or use for agriculture or whatever purpose you want. Notice that the osmotic pressure for seawater is about 22 atmospheres naturally. And if you want to do this commercially, you would need a much higher pressure, 50 atmospheres of pressure, to get your fresh water. Obviously, if you're doing it by hand, you'd only need to have a little bit more pressure than 22 pressures to make the little bit of water come out on the right side for you to drink. It says here that you've got more than 15,000 reverse osmosis plants in operation worldwide. And I'm sure since the printing of this book that that's many thousands greater than that. The one engineering problem I should mention is going to be this, and that is that your membrane here, we want to invent better and better membranes that can withstand this high pressure. You don't want the membrane to rupture. If you're unaware that the membrane ruptures, then all the stuff on the left side is getting through the break in the membrane to the right side, and you could end up drinking contaminated or salt water. So we're always trying to come up with better and better membranes. Notice also that this requires energy to push down on this piston, either by you or by a machine. And of course, that's going to require electrical energy on a commercial scale. It's not naturally occurring or spontaneous, and that's why it requires energy. A little bit more on that. Osmotic pressure as a colligative property is a much easier way to determine, for example, the molar mass of something, because you can get it's much easier to measure changes. When we're using the colligative properties of a change in boiling point or a change in freezing point or even a change in vapor pressure, those amounts, those changes are usually very, very, very small for the amount of solute that you're adding to the solvent. But with osmotic pressure, you can get very large measurements that are much, much easier to measure. And we'll do some math problems to prove that situation. By the way, if we take a fresh egg down here and we place it in dilute acetic acid, the acetic acid will react with the calcium carbonate to take away the shell, but not the membrane. Remember, an egg, in a sense, is a large, almost like a cell, and that membrane stays behind, even though the shell around the membrane is now gone, and therefore water can diffuse into the egg. The concentration of water inside the egg is low. The concentration of water outside the egg is great, so water will diffuse into the egg and the egg gets bigger. in part C, this last picture, if the egg with its shell removed is placed in concentrated sugar water, then the egg is going to get smaller. And the reason for that, of course, is you have high concentrations of sugar on the outside of the egg, which means by comparison, the concentration of water outside the egg is lower than the concentration of water inside the egg, which by comparison is higher. So water diffuses out of the egg and it shrinks or shrivels. Cells do the same thing. Let's go back to that picture real quickly. If you think about the egg as being a cell, it's possible that if your cell is in pure water, it's going to swell up and it could burst, okay? And that burst could be called, if it's a blood cell, it's called hemolysis. And that's why your IV solution needs to be isotonic with your blood, which means to have the same iso concentration as your blood has, colligatively speaking. And over here, if you think of the egg as being a cell, and if your IV solution is too concentrated, has a higher concentration than the blood itself, then the water is going to flow out of your cell, your blood cells, and that's going to shrivel up, which will destroy the cell. And the vocabulary word for that is crenation. All right, a couple of math problems. In this particular problem, you have polyvinyl alcohol, which would have a big molar mass because it's a polymer, 28,000, and you're going to dissolve a whole lot of that in water to make a solution. You're given the volume of the water. You're also given the temperature, a little bit above room temperature. And so in order to find your concentration in molarity, you've got to take your moles, and here's where you're going to find your moles, and you got to divide, let's fix that. Your moles are actually converting your grams into moles by dividing by the molar mass, and then you divide that, the number of moles, by the volume in liters, and that's how you find C, the concentration. Then that number comes in here. Here's our ideal gas law constant, because evidently we want the answer to come out in millimeters of mercury. And here's my 27 Celsius, 300 Kelvin, and we're going to get 0.011 atmospheres of pressure, which is 8.2 millimeters of mercury. And of course, that's a large enough value that you can actually measure that value. You can get out a centimeter stick and measure 8.2 millimeters of mercury. This next problem, we have a solution with 1.25 grams of oil of wintergreen. Again, this is a non-polar liquid. We'll worry about polar solutes later. This is a non-polar solids, grams. And we're going to be dissolving it in a non-polar liquid, benzene. There's my solvent. Make sure you keep straight which is the solute, which in this case is the oil of wintergreen, and which is the solvent, the benzene. And I guess if it's an oil of wintergreen, it would be a liquid solute. And when we go to solve the problem, I call this a 3M problem, because you're going to find, first of all, your molality. And once you find your molality, then you can plug that in over here. Molality is moles per kilogram, and multiply by the kilograms of solvent to get your moles. There's your second M. And once you have your moles, you put that down here and divide it into your grams to get your molar mass, which is your third M. So you go from molality to moles to molar mass, a 3M problem. And of course, one of the powerful uses of chemistry is to be able to identify the molar mass of something. Because once you know the molar mass, you've narrowed down oftentimes to just one possible substance or compound that has that particular molar mass. Here's another problem. Beta carotene is the most important of the A vitamins. You can find it, for example, in carrots and other things that are orange. It's also a pigment that's present in leaves. And so in the fall, when the chlorophyll, which causes the green color for leaves, begins to break down before the other pigments do, when the green is gone, it leaves behind things like the orange color from beta carotene or maybe the reddish color from xanthophylls. That's why the leaves change color. In any case, we're going to calculate again what is the molar mass. And so identify what the solute is and identify what the solvent is. Solute is your beta carotene. Your solvent in this case is the chloroform. And so the first thing we want to do, another 3M problem. In this case, we're going from my molarity, which is my concentration, to my moles, to my molar mass. Another 3M problem. So the first thing we're going to do is find my concentration. And the way we're going to do that is by taking my pressure, capital P, my pressure, and I want it in atmospheres because I'm using this constant right there. So I convert my millimeters into atmospheres, 760 millimeters of mercury per 1 atmosphere, and divide by my R constant and my temperature to get my molarity. And there often in this situation use C for concentration instead of capital M for the molarity. Once I have my molarity, I plug that in down here, multiply by the volume. Once I have my volume and multiply those two together, I get my moles. And then I take my moles and divide it into the mass that's given to me to get my molar mass, 538. And that's it for osmotic pressure.